UAVs are used today to complete a variety of tasks, including, and not limited to, disaster relief, 3D mapping, and delivering products. UAVs are relatively new technology and pose several challenges in their continued development. These problems can include the inability to recognize and avoid other airborne objects, vulnerability to GPS jamming and hacking, which has the potential to lead to cyber terrorism, and a lack of technological and operational standards needed to guide safe deliveries of packages to their desired destinations. As the technologies of UAV continues to develop, control engineering has the capability to demonstrate better performance by identifying current problems and finding a technological solution.
Our goal is to safely maintain the quadcopter at a constant height, which in turn will allow for the safe delivery of packages. In order to do this, the upward force produced by the four motors will be the variable controlled, and the height of the plant will be the output variable. The image on the left represents the mechanical system of our plant. FR of T represents the force from the rotors. H of T represents the height. Fg of T represents the force from gravity, and B represents the damping ratio. The image on the right represents the block diagram of our plant. Fg of S is represented as a disturbance and is gravity impacting our system. Fr of S is the force from our rotors on our system. G of S is our transfer function, which will be calculated shortly, and H of S is our height output variable.
After we have our model and block diagram for the UAV, we can get the impedance network for the UAV. Here is the equivalent impedance network. From here, we can simplify it down by using some algebra, and we get the transfer function of 1 over ms squared plus bs. M in this case stands for the mass of the UAV, and B is our damping ratio. From there, we can get a step response, which relates applied force to quadcopter height, which should look like this. Although we used the transfer function 1 over ms squared plus bs to actually get this step response, in our case, we're going to use these values to show what our UAV will be like. We will use a mass of 0.5 kilograms, a damping ratio of 1, and then the force of rotors is going to be 50 newtons, and our force of gravity is going to be, of course, mass times 9.81 meters per second squared.
The open loop plant takes in an input which is upward force, indicated right here. Since this is an open loop system of the second order, there will be some overshoot expected. This means that the open loop system is unstable. Because the system has no control, therefore it is BIBO unstable. For example, if one examines the open loop poles of the system, which is in the denominator of the transfer function indicated right here, there will be poles at 0 and negative b divided by m. B is the damping coefficient and m is the mass of the UAV. Then b and m should be positive numbers, which makes negative b over m fall in the left half plane, while 0 is on the imaginary axis. Since there's a pole on the imaginary axis, the open loop system is unstable. The open loop plant will experience disturbances from outside forces. The primary force impacting these functions of the system is gravity. When implementing a design for the plant, disturbance from the gravitational force will have to be accounted for. This is shown in the diagram below. This is the example of the PD controller that accounts for the force of gravity acting on a UAV.
Once we've modeled the correct step responses from the MATLAB and Simulink, we can note the root locus plot. First, we can note that the percent overshoot is less than 10%, denoted by these lines, and then we add a real 0. And this can be tuned in order to find the right C of S function, which gives us the value of 0.15986 times S plus 6.256, which is correct because our KD value is 0.15986. In order to verify that this is correct again, and we have the right transfer function for the step response, we can note that the Nyquist diagram never encircles -1 and is stable. Then we can also note that there's two other step responses that we can find from the transfer function, from dy to y and from du to y, which shows that there is no disturbances that will affect the closed loop system because it has been accounted for. This is called disturbance rejection, and because we have accounted for the gravity, it will not affect our references because we have the step input response.
The PD controller was used to implement a feedback. The feedback's purpose is to maintain the drone's height in the atmosphere. The transfer function for a PD controller was calculated to be this. Once we had calculated our transfer function for our PD controller, we implemented it into our Simulink block diagram, seen here. Additionally, we implemented our transfer function for our PD controller into MATLAB. We assumed values of a mass to be 0.5 kilograms, the damping ratio to be 1, our Kp value to be 7, and our Kd value to be 0.159. These values were tuned so that our requirements were met. Our requirements were to have a percent overshoot of less than 10%, a rise time of less than 1 second, and our steady state error to be equal to 0. Our results from Simulink are shown below. Here we can see that our transfer function and our PID controller accurately represented what we wanted it to.